A recording in progress.
Hey guys, quiet please. We're starting. Thank you. Okay, so let's go over the homework. Guys, I'm talking. Thank you. So thank you, Audie. Appreciate it. Yeah. All right. So number one, you have a weird function, the cube root of the absolute value of x. That's kind of a funny one. So the questions for 1, 2, and 3, and I don't know why that's a separate file. That's totally fine. The question is asking you to use a condition of continuity at a point. Find a definition of the right-hand left-hand derivatives. Sorry, and the formal definition of the right-hand left-hand derivatives. Analytically determine if f(x) is differentiable at the indicated point. So yes, of course, this is going to be continuous at 0. I don't see why it wouldn't be, because 0 exists, right? F of 0 is fine. The limit's going to be 0 anyway. That's going to be fine. And the limit equals f of 0. That's going to be fine. So the continuity is okay. When the continuity fails, you don't have to go any further. You can say it's not differentiable and move on. But if continuity is cool, then we move forward and say, now let's find the right and left-hand derivatives. To do that, what we would do is we would do the formal definition of the left and right-hand derivatives. So just to kind of walk you guys through it again. The left-hand derivative, h put 0 from the left. Right-hand derivative, h put 0 from the right. Remember, h is going to be slightly negative here, h is slightly positive here. And remember, you're doing 0 plus h minus f of 0, f of 0 equals to 0. And then here replace h with 0 plus h. Excuse me. So in absolute of h, which I know is 8, but because it's approaching 0 from the left side, oh, right. Let me take this back. This is a piecewise function, right? Absolute value we treat like piecewise. So that's what I have to do. So actually, I didn't write the piecewise function. We should actually do that. So if you let f of, I don't know, f of h, just say whatever, or f of x. We know this is true, right? So you're going to replace h with negative h if you're doing the left side, right? We're in the left side of it, and then of course you get this, and you work it all out. And if you plug in 0 for h, or something close to 0, like a very small number that's negative, overall it's going to be negative infinity. Here, overall, it's going to be positive when we work out the right-hand derivative, because h is slightly bigger than 0. So f of h is h. Work it out. You want to h to 2/3, and that should be positive. I don't know why that's a negative. That should be positive. So anyway, what's happening is that the left-hand derivative is going towards negative, the right hand is going towards positive infinity. What happens when that? Well, what do we call that when that happens? We call it a cusp. Exactly. They're both positive here, both negative infinity. It's vertical tangents, right? Or both finite numbers that are not the same, they have a sharp point, right? So that's a cusp in that case. We'll go through the other ones a little more quickly. Now you get the idea. Now in this case, it's not continuous. F of 0 is 1, but the limit is going to be 0 because inverse tan is 0, because you're looking at the approach for limits, right? When you're doing the left-hand limit and right-hand limit, you're not going to plug in 0 straight up to the function. You're going to see what happens to y, or f of x, as x gets closer from the left side, x gets closer from the right side. Really just look at the inverse tan of x function, and that's 0. Because you're not continuous, you're not differentiable, you move on. For number 3, we got a true piecewise function, root x and 2x minus 1. And usually as a quick check, I mean, if you really want to save time, just plug 1 in. If they're both the same, you know it's going to be continuous there. So I know it's continuous, but just to be formal about it, fine. F1 is 1, left hand limit is 1, right hand limit is 1. The limit equals F1, so we're continuous. So then we proceed with the left and right hand derivatives. Left hand derivative, you're going to focus on root x. Right hand derivative, you're going to focus on 2x minus 1. When you work each one out, they're different numbers. Because they're different numbers, but finite, you're going to say it's corner. It's a corner there. You don't have to say sharp corner. Corners are sharp anyway. I just like saying sharp corner. Just call it corner. It's good enough. Okay. But I will say this. Somebody one of these 3, I'm definitely going to put on our test next week. And we'll talk about the test. I'm going to design it tomorrow morning. So when I see you guys Friday, I'll tell you guys all the nitty-gritty details about the test, what to expect. But something like that, I'm probably going to put, because I like this question a lot. 4 and 5. That's pretty easy. Just looking at the graph. Tell me where it's differentiable, tell me where it's continuous, but not differentiable. Tell me where you need a continuous nor differentiable. Okay, go ahead. Guys, quiet, please.
Like, do you put endpoints as like not the non-differentiable?
Oh, for this problem here?
Yeah. Or like in general, do you want to do?
That's a great question, actually. Usually we don't on the AP because there's a debate, like some people say should you, should you not. It's a fantastic question. And you have these like math professors and veteran math, high school math teachers that like geek out over it, like in Kansas City when they grade AP exam in June. I've never done it, but I've heard people have done it. And it seems kind of a frivolous argument, to be honest, but they in order to mitigate that argument, they just say use open intervals. So I think for what I will probably do is I'll say, hey, give me the interval where it's differentiable, give me the open interval. So that way there's not that debate. So we'll just keep it open. So that answers the question.
Well, for like part C, I think that's like,
Yeah, so we'll just keep it open because corners are kind of funny, or endpoints are kind of funny with differentiability. Usually there's a lot of theorems that we'll see down, well, not in this class, but afterwards. Where sometimes you just use an open interval for the differentiability part of that theorem. So Captain, go ahead.
So like what you're saying is like, it's not good for the, but like a very, very important use on that.
Exactly, right. So let's look at the answer key for this one. Let me pull up the answer here.
But for like B, you wouldn't include the endpoint in continuous but not differentiable, right?
Hold on a sec. Let me take a look at it. So they say all points from -2 to 3. Okay, they actually included -2 and 3. I'll just keep it open. They include it, but obviously you're not continuous. Sorry, you're not differentiable at discontinuities and at corners. So -1, 0, and 2 are pretty obvious that you're not differentiable. You're definitely continuous at -1. But not differentiable there because that's a corner. And then for C, neither, that's at 0 and 2, right? So that's pretty easy. Yeah, I see what you're saying. So like, because we're saying it's not differentiable, but it's continuous there. So you're saying for part B to include -2 and 3. Is that what you're saying, Captain? I will say this. Here's okay. To mitigate this situation, I'm gonna say focusing on the open interval from -2 to 3. So we're not even looking, we're not going to consider it for those parts. Yeah, so we'll start the question by saying that, and then you don't have to worry about it. But that's usually what they do in the AP exam. They just say focusing on the open interval from -2 to 3. Tell me where it's not continuous. Tell me where it's blah 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 whatever. So yeah, that way we don't have to worry about that debate. For 5, it's got a cluster at 0, so obviously you're not going to include 0 for the differentiability part, and that's what we got. And of course, there's nowhere where it's neither continuous nor differentiable. For 6, sketch a graph of F prime. Well, that's a fun one. There you go. It's a bunch of straight segments, right? Well, segments are straight regardless, but how do you know you're gonna have corners at x equals -2 and x equals 2? Whenever you have jump discontinuities on the F prime graph, so I think hopefully we're seeing this connection now. This is the part that's a little mind bending, but it's huge. It's a huge part of calculus. The AP exams, they love this kind of stuff. And you take the F prime graph and interpret it correctly, because clearly this left-hand derivative is a finite value, right? This left-hand derivative is going to be -3. This right-hand derivative x equals -2 is -1. Those don't equal each other, therefore it's not differentiable, but they're finite values, right? So instead of giving a number, like, oh, the left-hand derivative is this, right-hand derivative is this, we're doing it analytically, we're now interpreting it graphically. The left and right-hand derivatives are not the same at x equals -2. And the finite values, that's what's making corners, right? Likewise here, the left-hand derivative at x equals 2 is -1, right-hand derivative is +2. Those are finite values not equal to each other, so that same thing's happening there. Then how do you actually get the exact y values? You got to use this correctly. So to show you how I do that from scratch, here's what I do. So you have this, right? 0, 1. And then 1, 2, 3, 4. Okay, I agree. These grids, right? That was foolish of me. Here we go. Much better. Much better. I like that. Okay. So anyways, you have this. Now, before you get to so from -2 to 2, the slope is -1. So I'm gonna make sure I use a slope of -1 until I get to 2. And likewise here. Does that make sense? Right? And then I'd say, okay, well now the slope is +3. So make sure you use a slope of +3. Like that. So that would make sense. I have a point at -2, 3. Then here I have a slope of 2. So at x equals 2, yeah, I have a point at 2, 1, 2, -1. So that's why that's my answer there. So that's how you can generate those more accurately. But I like that question a lot too. It's a great question. And finally for 7, given f(x) equals 1 over x, explain why it's not differentiable x equals 0. Well, you have infinite discontinuity, right? So forget about it. Right, that's pretty obvious. They have a vertical asymptote, no good, right? And it's not defined there anyway. Use a calculator. Okay, I didn't teach this to you guys yet. So this might be a nice little segue to what we're going to do in the notes in just a couple minutes. If you didn't do B and C, don't worry about it, because I actually should not have assigned that the more I think about it. But here's what you do. You go to the calculator. To call up the derivative, you hit alpha window. That's my favorite place to do it. Option 3. Or hit the math button and go down to, I think, option 8. It's right there. And it's going to put it in this kind of notation. So I'm going to do 1 over x for my function side. And I'm going to type in x equals 0. Now it actually gives you an answer, which is funny. Because we know there's a vertical asymptote there. Why is it giving me an answer? It's giving me an answer because the algorithm the calculator uses, if I'm not mistaken. Yes, 100%. Yes.
What did you say were the buttons?
You can do math, option 8, or alpha window, option 3. Alpha window is my favorite because there's other stuff there too. So, but anyway, it's doing this, guys. If I'm not mistaken, I think that's what it's doing. I think it's doing f of 0.001 minus f of negative, over 0.001 minus negative 0.01. This is called, in case you're curious, this is called symmetric difference quotient. So it's not quite, yes, it is an average rate change. So 1 over x, we know is this, right? So the algorithm calculator uses is figures, okay, well, here's that negative 0.001. Here's that 0.001. Well, what's 1 over 0.001? What's that going to be? 1,000, right? Yeah. And 1 over negative 0.01 is negative 1,000, right? So what do you got yourself here? You got yourself 2 thousandths over 0.002, or 2 times 10 to the 3rd power, or 2 times 10 to the negative 3 power. That's 1 times 10 to the 6th power. That's where you get 1 million. That's where you get 6 zeros. 1, 2, 3, 4, 5, 6. Of course, that's not right. That is incorrect, right? We know the answer is supposed to be not differentiable or doesn't exist or whatever, right? We know that. But this is what the calculator is doing. So now you understand the algorithm. So it's not truly doing it analytically. It's doing an approximation. That's how it does it. So nice little segue to what we're going to do in just a little bit. But what does the answer to the calculator give? Is it correct? No. They show analytically the symmetric difference quotient, which I just showed you guys. So the answer is all right here. So hopefully it all makes sense. I mean, I did give you guys the answer key anyway, so hopefully you're able to make sense of it. So that kind of might help the notes a little bit. So any questions at all? No? All right, let's move on. Let's go to the notes. Then we'll hopefully do the rest of the homework afterwards. Yeah, so here's the deal. We're going to pick it up from the middle of page 5. You can find numerical derivatives. I emphasize the word numerical because it's not doing it analytically. So like x cubed at x equals 5. Now, the old school way, this is how before the calculus went through an upgrade, I think in 2009, 2010, where they have the more symbolic stuff. Before you actually, it looked like this. And the RV, you had to know the first argument was a function. The second argument is that you do with respect to what variable, with x. And then the third argument was at what number you're going to plug in. That was the old operating system TI-84. But the way the new operating system works, it's actually symbolic, which actually is better, right? You know, you want to be able to read it that way. And there's a vertical line that comes down after x cubed, and that's just showing like a partition, like, oh yeah, here's a partition, and now plug this x value into my derivative. The calculator cannot do the variable expression for the derivative. It's not going to tell you, I know it's 3x squared. It's not going to give that to you. The TI-4 doesn't have that sophistication. If you have a TI Inspire or a TI like 91 or 92, it will do that. Those are actually outlawed from the AP exam because they know that, or banned, or whatever word you want to use to describe that. If you, let's work it out. If I work it out, it's pretty simple. I like using alpha window, that shortcut, option 3, d dx, x raised to the third power. And because I know the derivative is 3x squared, if I plug 5 into that, I should get 75, I believe. Yeah. But why does it say 75.001? Because now we know it's doing an approximation, right? I mean, it's a pretty darn good approximation, but it's doing an approximation nonetheless, right? So that's why it gives that decimal, just so you know. But truly, it's 75. And if you are curious about the old operating system, how it looks, you switch to classic. And if I hit math, option 8, see how it does that? And I have to like type it in like that. It's just such an old school way of doing it. But just so you know. And by the way, the calculator is absolutely crucial for the AP exam. There's actually some questions that are calculator required, meaning you are SOL. You don't have your calculator for the, and again, AP is a year plus away for you guys, but, and there's actually a certain, not pedagogy, but a certain like skill set that comes into knowing how to use it correctly to decipher these questions and make sense of them. So we'll make sure we'll spend more time with that over the next few weeks before we end this class. Yeah, and here's what it's actually doing, right? I already told you guys this is what it's doing, right? Now you know whatever x value you're looking at, like what you're evaluating at x equals 1, then you're going to put 1.001 and 1 minus 0.01 or 0.999, and you divide by 0.02. In case you're curious, a somewhat better approximation is this right here, the one right below it. But what is it really doing? You're picking two values. So what n derivative is doing in the calculator, the numerical derivative, it's doing a value a little bit to the left as a point of interest, a little bit to the right. And if you draw a secant line from RQ, okay, that's not quite straight, but it's okay, just go with it. And you draw one at P. Oh, pretty close, right? We're pretty close. This is somewhat better if we did it like this. But anyway, but neither is the limit though. They're really just approximations. And what we get if we substitute H equals, what do you mean by that? Let me look at my filled out notes for that part. Oh, 0.01. Okay, well, that's weird. Well, I think you just get, yeah, you just get the slope of PQ, right? Yeah, that's just a weird question. What would you get? Yeah, just get the slope PQ. So again, it's just close enough to the actual derivative. Does that make sense? What's happening? The calculator? Okay. So let's do it again. Use your calculator to graph that. Okay, we're going to graph the derivative of that. Okay. Well, first off, what was the derivative of x cubed? 3x squared, right? We know this now. So this right here will be 1/6 or x squared over 2. So that's what I expect it to look like. And if I were to plot it, let me put 1 and 2, 1 and 2, -1, -2. I know to expect that, but what I could do is this. If you hit alpha window, option 3. Let me switch back to the new operating system. Alpha window, option 3, x, and then I do x raised to the third power divided by 6. Now here's the funny thing. When you graph this, yeah, see if I put x equals
number, like 2 or 1, what do you think's in the graph if I do that? Actually, just a horizontal line. Because that's gonna be a numeric value, it's just gonna graph y equals that number.
So you don't want to put a number, you have to put x because you want to actually compute the derivative for every value of x in the window. The window that I have looks like it's normal. Okay. And it's gonna be kind of slow, right? Because it's computing all those derivatives. It doesn't do it very quickly. It's kind of slow. I mean, if I were to turn this off and actually graph x squared, gosh darn it. Wait, geez. Wait, what's going on? X, oh, there we go. X squared over 2. See those more quickly, right? So anyway, it's gonna be a little bit more labor intensive. And then I don't know what's meant. What can we do to help identify the graph of f prime? I think slopes of tangent lines. Oh yeah. Oh, I see what's asking. Got it. I didn't understand the question. Okay, let's come back here again. What can we do to help identify the graph of f prime? It says we get some points in the graph, second trace value. Okay, so let me do that. So if we get some points in the graph, let me turn this one, let me clear this one here. Yeah, so if you were to hit second trace value, like at x equals 2, my derivative is 2, right? Or if I do this, at x equals, say, 4, my derivative is 8. So you could always hit second trace value, second trace value to identify the numerical value of the derivative at various x coordinates. Okay. Nothing could have done too. If I just graph the original function, right? X cubed divided by 6. And if it's second trace, pick option 6. Now you know what that means. And type in 2. It does give me the derivative. Or if I do it again and type in 4, even though it's 4 comma whatever, it doesn't show in the graph, but it will give me the derivative at that point. So same, it's second trace, but option 6. Yeah, option 6. That's if you put into the original function, right? Right. But if you want, if you have the derivative graph, then you just find the value at that point. Okay, note of caution. The calculator can be misleading, as we already saw. So this one we know is this, right? This graph here. We know this. F prime is 0. We know does not exist, right? But the calculator is going to say this. It's going to say 1,000, which I know is not true. And that's because the symmetric difference quotient is going to be 1,000. Because the calculator is doing this. It's finding that slope. That's what it's doing. Okay. Now that we can graph the derivative function in our calculus, let's go back to the problems on cusp and vertical tangents. Let's look at example 7. Let me size this up a little bit. Okay. So let's graph this. Yeah, let's graph the original and the regular one. We'll see that right now. Here we go. So usually when I do this in the calculator, as a good habit, you should start establishing these habits now. Is I'll do the original as y1 and raise that to 2/5. And then I'm gonna hit alpha trace. Let me quit. Sorry. I'm gonna hit alpha window option 3 x. I'm not gonna type the equation with alpha trace y1. This is all being recorded, by the way. This way it knows to look at y1 and do the derivative. Let me turn off the second one, just do the first one. So you always toggle it like that. So it looks like there's a cusp at x equals 3, right? And then I'll graph the derivative with it. It's really slow, right? Why do you think it's doing that? What do you think it's doing there? Yeah, it definitely the derivative gets close to infinity or negative infinity at x equals 3. Exactly. That's exactly what's happening. So if I graph it, yeah, it might be a little too high. And then here you have a vertical asymptote there. So you have to interpret this correctly. So the way we see this, we definitely have a cusp. And that's because the left-hand derivative is negative infinity. The right-hand derivative is positive infinity. And on the f prime graph, the y coordinates are f prime values. Yeah, good.
Oh, yes, the cusp doesn't require. So I was gonna, the
Hmm?
tangent line, yeah, where it's like the, like kind of like a, root 3, it's like cube root kind of graph, looks like, an F line. And then, yeah.
What do you mean cube root?
Or.
That's a vertical tangent. That'd be a vertical tangent.
Yeah, prove that as, notice because if you just go off like derivatives, then it would also be like that, the function with the same derivatives.
Wait, say again? Rational.
A rational function would also have like negative infinity and positive infinity for the set side, both like the same infinity.
No, rational functions, no. No, because you have this at the vertical asymptote, or I'm confused. What you're asking?
One like the derivatives be like both the same negative infinity.
At where on the rational function?
At x.
But what's your function that you're looking at? Are you looking at 1 over x or? Yeah, but you're not continuous. You're not differentiable.
So for I'm saying like for tangent lines, you have to prove that's continuous.
Oh, I see what you're saying.
Just go off the-
Oh no, of course you want to prove this different. Yeah, of course you want to prove the continuity part. Yeah, of course. No, right. I see what you're saying. At 1 over x, sure. Yeah, it is negative infinity on each side, but it's not a vertical tangent because you're not continuous there. Right. That's the reason why you're not. That's the reason why you don't not differentiable. You're not continuous. You have to establish that first. Right. Right. I see what you're saying now. Okay. Yeah, I think that's all there is to it. I don't think there's anything else I want to add to that. Look at my filled out notes here. Yeah, I mean, we don't actually have to go through the motions. I think you guys get the idea. So Let's keep moving. All right. The alternative definition of the derivative. Okay. So here's yet another way you can look at it. So we've already done this one here. This one is going to be, guys, quiet, please. Thank you. But you have the same thing here. So the slope of the secant line, actually, I just did the slope of the tangent line for you guys right here. And the slope of the secant line is just this. But what happens to the a's here? Yeah, they cancel out. And then for here, if you do this one, that's going to be the limit as x approaches a of f of x and the slope of the secant line is just f of x. And what's happening here is you want x to get closer to a, right? As x gets closer to a, it becomes more of like a tangent line. So it's just yet another way of finding the derivative. That's all it is. That's all you're doing. It's called the alternative definition. So you just want to be able to recognize that. That's really the key point here. You want to recognize that. So let's move on to this example. Then we'll talk about IVT for derivatives, and then we're all done. Okay. So f prime of x is going to be the limit as x approaches 11 of f of x minus f of 11 over x minus 11. And just so you understand graphically what's happening, here's what's happening graphically, right? We're trying to find that slope, right? That's all this represents. It's just trying to find the slope. And actually, let me change that x to an 11. My bad. We're trying to find f prime 11. So you just do it. You go through the motions. What's f of x, guys? And what's f 11? 3. Good. Yeah, then you work this out. So I'm getting x minus 2 and then plug 11 in. You get 1/6. Which makes sense. Looks like it's 1/6. So we're good. So you'll have a chance to do homework. There'll be an opportunity for you guys to do that. And I may ask that too on our test. Like, hey, I want you to show me this process. Okay, I'll give you guys a moment to copy that down. All right, last one, last page. Okay, let me show the filled out version of this. Okay. Let me talk you guys through the IVT for derivatives. So it's no different than IVT for just functions in general, right? So say A and B are 2 points interval, and F is differentiable in that interval. Then F prime will take on every value between F prime and F prime B. That's what it's saying. So, for example, I'll just kind of do a quick sketch here. So this is A, so this is B. So you got a nice smooth curve here, right? And I don't think we include I guess we didn't do that. Well, anyway. So basically, whatever the lowest, so whatever F prime A is, I mean, I'm just gonna guess, like what F prime A is like 4. And F prime B, I was like, say 1. But any value between 1 and 4, any derivative value between 1 and 4 can be had in this interval here. Anything in between can be had. That's what it says. So it reminds us of IVT for continuous functions. The function that is a derivative exhibits IVT behavior, even if it's not continuous. So let's take a look at example 9. Suppose you're given a mystery function f and you're told that f is differentiable on an interval containing -2 and 5. You're also told f prime -2 is -0.8 and f prime 5 is 2. So can the derivative equal, say, 1 when x between -2 and 5? Yes, 100%, right? Can it equal -0.3? Yes. Can it equal 0? Yes. So how do you know? IVT for derivatives. One important key piece of information you need to know about this, that f was differentiable in that interval. If it's differential, of course, it's continuous as well, right? We know this. And will there be some x equals c and -2 5 such that f prime c equals 4? Could be, or maybe not. Like, look how I drew this one. Do I have a derivative that's 0? But it's 0 between 1 and 4 here? No, right? So it could be. I mean, if it's outside the range, it could be. We don't know for sure. It's not a guarantee. Does that make sense? Right. So just very similar to the IVT for continuous functions. And then let's look at an example here really quickly. Let me expand this just a tad. So given a function is continuous on that interval, and g prime 3 equals -4 and g prime 7 equals 1.5, will g have a horizontal tangent for some x? Now, we threw it into a loop here. Did it say g is differentiable on interval? Or did it just say it's continuous? Just said continuous. So it's kind of sneaky. You have to use kind of that legal language. You have to read it very carefully. We don't know. We really don't know. Maybe. No idea. So major takeaway, this theorem would be unnecessary if all derivative functions were continuous, then fine. But some derivative functions may not be. So we can't assume f prime is continuous. The f prime graph itself, we can't assume that. Now, if they say f is twice differentiable, then here's the deal. This is kind of interesting language that's used often in the equation. Twice differentiable means you can do the derivative twice. It means that after you do the first derivative is continuous itself. Because in order to do the derivative again, you need a continuous function, right? You need constantly to have the derivative. So f prime, of course, is fine, right? Because f is continuous. But f double prime is fine too. If you want to find a second derivative, that's because f prime itself is continuous. When you told someone twice differentiable, what it means that all f prime values exist. There's nowhere where it's not differentiable with the first derivative. That's what that means. Does that make sense?
Are these notes?
Told you, yeah. Yeah, so what it means that you could well, you do the derivative once, right? Okay, well, let's look back at here, I'll give you a good example. I probably should have done this. Okay, I can do a derivative because it's continuous everywhere, right? But how did that derivative look? It was kind of like this. Remember we drew like
like something like this here, something like this here, and something like this here, like, yeah, something like that, right? So this is my F prime graph. This is my F graph. But here's the problem. Is this F prime graph continuous everywhere? No. So I can't find. Like, there's gonna be some places where F prime won't exist. So this is once differential. Because there's definitely a couple places that will have an issue, right? But left hand is nice and smooth. My prime graph will probably be something kind of like this, I'm guessing. So all these F guys exist, right? Now, is there anywhere here where it's cornered or discontinuous? This is nice and smooth, right? So can I do this again?
Yeah.
That is done by twice the front. So now if I do this one, I think it's gonna be a line, if I'm not mistaken. That's what's meant by being twice differentiable. So IVT would be cool with this for derivatives because I don't have any issues. I don't have any place where it's not differentiable.
That's your twice differentiable for IVT.
Correct, yes. Well, I mean, yes, in that interval, right? So that's what's meant by that. Yeah, good. Yeah, then that would be a flat line. It used to be horizontal, but we usually don't go that far. Usually we just go second derivative and that's it. Man, go ahead.
Twice differential relates to base side.
So if you're twice differentiable, that means that IVT for derivatives will be fine everywhere. Any interval you pick. All values will be cool. Sorry, I didn't make that clear. That's a great question. NAS a great question. So what does that really mean? It means that you don't have to have a specific interval. IVT for derivatives will work everywhere for a function that's twice differentiable because you're not going to have any issues at all. Correct. Yes. Or if the function itself is twice differentiable, then the IVT for derivatives will work everywhere. Everywhere, right? Because it's gonna be fine.
If the function isn't, then we have to include that part.
Well, then you'd have to make sure that you're given a specific interval where the derivative exists. You have to be told that. So yeah, you can see the theory is coming into it. So this is good. Now you're starting to see some of the theory. And non-AP calculus or like business level calculus class, they don't get quite into that theory here. We got into it today, which is good. I like that. That's very good. All right. I think we're all set. That covers all the notes. I'm going to stop the recording.